All right, so far in this module, we've talked about algebra of functions, composition of functions, and we've talked about inverse functions. And those topics usually go together with the next thing and the majority of this module, which is going to be exponential and logarithmic functions. In this section, we're going to go ahead and talk about exponential functions and make sure that we understand exactly what they are. All right, so the first thing we're going to start off with is the basic exponential function. This was something that we explored last semester in intermediate algebra, but we're going to start with this one. All right, so a basic exponential function is going to be of the form f of x equals b to the x. And we do have some restrictions on b. The first one is b has to be a positive number, and it cannot be equal to 1. The reason it can't be equal to 1 is because then it's no longer exponential, because 1 raised to any power is just 1. And so that's a very boring example. All right, when we talk about exponential functions, the first thing that we have is the domain. Our domain is all real numbers. We can plug anything in for x. And our range is going to be y is strictly greater than or equal to 0. Y is strictly greater than 0. If you raise a positive number to any exponent, it is going to be positive, and it's going to be strictly positive. It will also never be equal to 0. When we talk about our exponential functions, we also have our intercepts. And so we have every basic exponential function has a y-intercept of 0, 1. And this is because if you raise any number to the 0 power, it's equal to 1. We already mentioned that our range is strictly greater than 0, which means that y can never equal 0. And what that means is we have no x-intercept. For exponential functions, we do have a horizontal asymptote. We've played around with these in our rational functions, but our basic horizontal asymptote is going to be y equals 0. Remember that as x gets really, really, really large, as x gets really, really, really small, we're going to get closer and closer and closer to 0. And by really, really small, I mean really, really negative. And so we do have a horizontal asymptote of 0. Now for exponential functions, we basically have two shapes. And the first one is if b is greater than 1. If b is greater than 1, we have our y-intercept of 0, 1. And what we're going to have is an increasing graph. And it's going to look hopefully something better than that. Okay. Our second option is if b is between 0 and 1. And just so you know, sometimes they denote this with a negative x as the exponent. And what this basically looks like is we have a decreasing curve. For both of them, we're going to get closer and closer to the x-axis, whether it be on the left side or the right side. All right, so these are our basic exponential functions. The second thing we can do is we can add in a multiplier. And so our other exponential function that we are going to consider is going to be f of x equals a times b raised to the x. We do still have the same conditions. We have b has to be greater than 0, and we have b cannot equal 1. And if you look at this, basically we still have the same things as we had before. We still have a domain of all real numbers. We still have a range of 0 to infinity exclusive. We still have an x-intercept of no x-intercepts. And we do still have a horizontal asymptote of y equals 0. The only thing that changes is the y-intercept. Instead of it being 0, 1, what it's going to be is 0, a. Whatever this outside number is your y-intercept. All right, so the next thing I want to do is I want to talk about a comparison between linear and exponential functions. Though they look nothing alike, there are some similarities between them. All right, so when we look at linear functions or linear equations, we have y equals mx plus b. And we have two basic things here. In our linear equation, we have a slope. And when we talk about the slope, this is a number, a constant, that is added or subtracted to each y value as you increase the x's. The second thing we have is the plus b. And the b is our y-intercept, or the initial value. All right, when we talk about exponential equations, we have things that are similar to this. The first one we have is b. b, we call this the base multiplier. And what it is it's a constant that is multiplied to each y value. So it acts similarly to the slope, but instead of adding or subtracting a number, we're multiplying the numbers. And we also have an initial value. We have a y-intercept, or an initial value, which is that number on the outside. So the number closest to the x is either going to be our slope or our base multiplier. It's what we add or subtract. It's what we multiply or divide. And the other number in our equation is the y-intercept. The other thing that we want to think of when we talk about exponential equations, when we talk about slope, when we talk about linear equations, we look for terms like increasing or decreasing. And when we say increases by, decreases by, this is something that we're adding or subtracting. Now, when we talk about exponential equations, the terms that we are looking for is double, triple, quadruple. These are words that imply that we are multiplying as we progress through our table, and that implies that we have a base multiplier. Value. All right, the first thing that we're going to do is we are just going to look at tables. And I want to know, is it a linear or exponential function? And then we want to go ahead and find an equation. All right, if we come to our first one, what we're looking for here is, notice that we have our x's are increasing by 1 as we progress through the table. And we want to know, what are we doing with the y's? And so to start off with, let's see here. How do we get from -3 to -1.5? We are adding 1.5. And we want to make sure that we do this all the way across the board. So if we do -1.5 plus 1.5, do we get 0? We do. If we do 0 plus 1.5, do we get 1.5? We do. And so what we have here is, this is linear, because we are adding the same number as we go through our table. We have a slope of 1.5, and we have a y-intercept of -3. And so we can use this in order to write our equation. I'm not going to write it in function notation because if you notice over here we have y equals. And so I'm going to rewrite this as y equals 1.5 x minus 3. All right, this is our first one. So let's go to our second one. Our second one, we start with our x's. And when we look at our x's, we see that we are increasing by 1 each time. Okay, that's the first thing that we want. All right, now the second thing we want is how are we changing our y's? And so when we look here, well, you can say, okay, well, we subtracted 12 to get from 16 to 4. But do we do the same thing across the board? Well, 4 minus 12 is not equal to 1. And so this is not linear. Well, it only gave us one other option. It has to be an exponential. Okay, so then let's go ahead and think about this from an exponential standpoint. All right, how do we get from 16 to 4? Remember, multiplication and division are basically the same operation. And so we're going to divide by 4. Do we do the same thing all the way across? Well, if we do 4 divided by 4, do we get 1? We do. If we do 1 divided by 4, do we get 1/4? We do. And if we go from 1/4, if we divide 1/4 by 4, we do get 1 over 16. And the main thing to remember is division by 4. This is the same as multiplying by 1/4. Remember that we copy, dot, flip the fraction, and so we have that division by 4 can also be represented by multiplying by 1/4. And that's the one that we want to use when we come up with our equation. Okay, so we have a base multiplier. What are we multiplying by? We are multiplying by 1/4. All right, we need our y-intercept, which is our a value, and our a value is 16. And so now when we plug this into our formula, we get y equals 16 times 1/4 raised to the x. All right, last one. Okay, for the last one, we have that our x's are increasing by 1. We're okay there. Okay, now let's go ahead and talk about our y's and see what we have. Okay, so let's start with linear because it's a little bit easier. But here, if we go ahead and look at how do we get from 3 to 4.5, we are adding 1.5. All right. Do we do the same thing across the board? And the answer is no. If we do 4.5 plus 1.5, we get 6, which is not equal to 6.75. So this one is also not linear. Okay, then, well, our other option is exponential. Okay, so now how do we figure out our base multiplier? Well, what we're going to do is, okay, I just want to know 3 times what equals 4.5. And you can pick any of these numbers to do this, but we're going to go ahead and divide 4.5 by 3. And what we because we are working with decimals, this is going to be the number we want to go with. All right, so just to check it, let's see what happens. What happens if you multiply 4.5 times 1.5? I do get 6.75, and so that checks out. And if you multiply that by 1.5, we do get 10.125. And so this is correct. All right, so we have our B. The other thing that we want is our A, which is our y-intercept. And our y-intercept is when x is 0. And so what we have here is y equals 3. That is going to be my A value. So this is exponential. And when we plug in our values to our formula, we get y equals 3 times 1.5 raised to the x. All right, that takes care of these first examples. Let's go ahead and continue and see what we can do next. All right, the next thing that we're going to look at is we are going to look at creating an equation given 2 points. And that's all we really need in order to come up with an equation. So we do want values of C and A in order to come up with our equation. So C here, they changed the formula for us. C is going to be our y-intercept, and A is our multiplier. All right, so when we look at the first one, we know what our y-intercept is. It is 4. And now when we look at this, we want to know, okay, what do we need to multiply by in order to get from 4 to 8? These are increasing by 1. So as we increase x by 1, what are we doing to get to y in order to multiply? And what we're doing is we're multiplying by 2. And so that is going to be our multiplier. And so what we have here is we have f of x is equal to 4 times 2 to the x. All right, let's look at our next one. Again, we want f of x equals c times a to the x. And we do have the y-intercept. Our y-intercept is 7, and so this is going to be our c value. Now we do need to be a little bit careful because we are not given f of 1, we are given f of -1. But the rule still applies. Is right here we have -1, 1, we have 0, 7, and as x increases by 1, how are we increasing the y? And we are multiplying by 7. And so our c value is going to be, our a value is going to be 7. And so when we write our function, we get c is 7, a is 7, and we have raised to the x. All right, let's come down to our last one. For this last example, we do not have our y-intercept. And so we need to do a little bit of work in order to find that. All right, so if we look at our table, what we have is when x is 1, y is 9. And when x is 2, y is 27. We do still have this increase by 1. And we want to know, okay, well, how are we changing from 9 to 27? We are multiplying by 3. And so all we're going to do is we're going to work backwards, okay? If we decrease x by 1, we get 0. And well, if we're multiplying by 3 as we move down the table, then well, we want to divide by 3 as we move up the table. And so here, if we divide 9 by 3, we get 3. And that's enough to come up with our equation. We have our y-intercept is 3. We have our base multiplier is also 3. And so our equation is going to be f of x equals the first 3, the c value, and our a value is 3, and we get 3 times 3 to the x. Now, they gave us very nice equations for these other ones, but this can be expanded in order where your c's and your a's are not necessarily the same numbers. All right, let's go ahead and continue on. We're going to do the exact same thing, except for we're going to be given an equation, a graph. And so for each one of these graphs, what we want to do is we need to determine our y-intercept, and we need to determine our base multiplier. All right, so for the first one, we have a very nice y-intercept. Our y-intercept is 1. And then we just need to find 2 points that are next to each other in order to figure out what our base multiplier is. And so here we have a y-intercept of 0, 1. And I'm going to go with -1, 2. All right. As we increase our x's, what are we doing to the y's? Well, here we are dividing by 2, and remember that dividing by 2 is the same thing as multiplying by 1/2. And so that is my base multiplier is 1/2. All right, so when we come up with our equation, we have c is 1 and a is 1/2. And we can go ahead and simplify this. We don't have to include the 1 in our final answer. We get f of x equals 1/2 to the x. Another way that you can write this is you can write this as 2 to the negative x. And just remember that negative exponents, we flip things around. And so we can flip our 1/2 and make this 2 to the -1 raised to the x, and then we just multiply those 2 exponents together. Me personally, I do like working with fractions. They make a little bit more sense to me. but these are the two different notations that you can use. All right, let's go ahead and try a couple other ones. Let's come over to the second example. Again, we want our y-intercept, and for this one, we have a y-intercept of 0, 3, which means that c is equal to 3. We do want to know our base multiplier as well, so we want to find another nice point. And the only other nice point that I see here is 1, 6. And so as we increase x by 1, how do we get from 3 to 6 using multiplication? We are multiplying by 2. And so that is my base multiplier. All right, if we go ahead and plug these in, we plug in 3 for C, we plug in 2 for A, and we get 3 times 2 to the x. Okay, let's look at a couple other ones. All right, for the next one that we have is my y-intercept is a little hard to figure out. I think I know what it is, but I'm not really sure. So we're going to go ahead and start with 2 points that we definitely know what they are. And the 2 points that I do know is I know that we have 1, 2, and I also see a point 2, 8. So as we increase x by 1, how do we get from 2 to 8? Well, this is multiply by 4. And so that is going to be my base multiplier. And what we can do is, instead of going from 2 to 8, well, let's go backwards now. And so if we want to go from 8 to 2, we want to divide by 4. And so in order to get to my y-intercept, I want to divide by 4. Now if we divide 2 by 4, we should get 1/2. That is our value for C. And so when we plug these into our function, we get 4 times, no, sorry. We want our C value first, our 1/2, and then we want 4 raised to the x. All right, last one. Let's see what we can do here. All right, we are going to start with, we have a nice y-intercept. The y-intercept is 0, 3. And so I know that C is equal to 3. Okay, now we want to figure out, okay, how do we get from this point, 0, 3, to the next point, which is 1, 1. So as we increase our x by 1, how do we get from 3 to 1? We are dividing by 3, which is the same thing as multiplying by 1/3. And so that is going to be my A value. A is equal to 1/3. So we can go ahead and plug these into our function, and we get C is 3, A is 1/3, and we have raised to the x. All right, that is looking at our graphs. The next thing we're going to do is we're going to go ahead and graph some exponential functions. We do want to, when we do our graphs by hand, we do want to label at least 3 points, and remember we do want our asymptote. All right, so when I graph exponential functions, what I always like to do is I only pick 3 numbers. And the numbers that I plug in for x is -1, 0, and 1. And if we go any further from this, our numbers get really hard to graph. Move that closer to my graph. All right, so what we're going to do here is, it doesn't matter where we start, but we know that anything raised to the 0 power is 1. Anything raised to the first power is itself. And anything raised to -1 is the reciprocal. And so these are 3 very easy points to calculate. And the reason that I don't go any further is because if we go out to 2, for instance, 3 squared is 9. I don't have that on my graph. And if we raise it to the -2, we're going to get 1 over 9. That's even harder to graph. And so that is why I stick with just these 3 points for pretty much all of my exponential functions. All right, if we go ahead and graph this now, we have 0, 1. We have 1, 3. And we have -1, 1/3. Remember that as x gets smaller, as x gets more negative, our fraction is just going to get smaller and smaller and smaller and smaller. And we are going to approach the x-axis, which is our asymptote. This is an asymptote of y equals 0. And just like we mentioned before, when we graph these, we want to make sure that we approach, but we don't touch, cross, or veer away from the asymptote. You do not have to draw your graph all the way to the edge, and that does get a little bit difficult on some of these problems. All right, I'm going to go ahead and label my points, and just to make it a little bit easier, I'm just going to label A, B, and C. All right, let's look at one more basic one. Let's come down to example B. In example B, we have f of x equals 1/4 to the x, or this can also be written as 4 raised to the -x. And again, I am going to pick the exact same numbers as I did before. I'm going to go with -1, 0, and 1. All right. Again, anything raised to the 0 power is 1. Anything raised to the first power is itself. And anything raised to the -1 is the reciprocal. And I was going based off 1/4 to the x, but same thing if you plug it into 4 to the -x. If you plug in -1, you get -1, which becomes a +1. That's where we get our 4. And if we plug in +1, we get 4 to the -1, which is the reciprocal. And so notice that we do still get the same answers here, no matter how we dress up this particular equation. All right, so if we go ahead and graph this now, we have a point -1, 4. We have a point 0, 1. And we have a point 1, 1/4. We do still have our horizontal asymptote at y equals 0, the x-axis. And when we graph this, this is going to be a decreasing curve. and we don't want to touch, cross, or veer away from our x-axis. All right, so these are our basic graphs, and this is something that we did in intermediate algebra, the last math class. Now, the next thing we're going to do is we're going to go ahead and take the things that we've talked about in this course and apply it to our exponential functions. And what we're going to do is we're going to use transformations. All right, the first thing that I want to do is I'm going to start with my basic function. And my basic function here is going to be 2 raised to the x. We just keep the base. All right, we're going to go ahead and create a table for this. And when we create our table, again, I'm going to use -1, 0, 1. And for this one, base 2, you can go a little bit further if you want. This is the only one that kind of stays relatively small for the longest amount of time. Now, if we're just looking at 2 to the x, and we plug in these values, 2 to the -1, we take the reciprocal, we get 1/2. Anything to the 0 power is 1. Anything to the first power is itself. And 2 squared is 4. We also need to remember that we have a horizontal asymptote of y equals 0. And now we're going to go ahead and use our transformation. Okay, so what we have inside our exponent, we have a -1. Because this is inside the function, this is horizontal. It is a shift. And we do the opposite of what it says. And so for this one, we want to go to the right. This means that all of my x's, I want to add 1 onto them. All right, so if we add 1 onto our x's, we get -1 plus 1 is 0. 0 plus 1 is 1. 1 plus 1 is 2. And 2 plus 2 is 4. No, 3. All right, the other thing that we have is we have a -2. This is outside my function. And so what this is a vertical shift. And we're going to go down 2. So we're going to take our y's and we are going to subtract 2. All right, for 1/2, if we subtract 2, we get -1.5 or -1.5, it doesn't matter. If we go 1 minus 2, we get -1. 2 minus 2 is 0, and 4 minus 2 is 2. The last thing that we want to do is we want to figure out, okay, what happens to the asymptote? And so we originally have a asymptote that is horizontal. It's going to be going side to side. And so my horizontal shift is not going to affect this. If I move it to the left or right, it doesn't really matter. For here, if we move it to the right, it's still going to be the same line. But if we move it down, that is going to change it. And so my horizontal asymptote is going to turn into y equals -2. So just like we subtract 2 from all of our y's, we subtract 2 from our horizontal asymptote. All right, we do want to go ahead and graph this now. So I'm going to start with my horizontal asymptote. We have a horizontal asymptote at y equals -2. And we want to plot our points. So we have 0, -1.5, 1, -1, 2, 0, and then I included that 3, 2 there. When we graph this, we get our exponential function, and it's going to look something like this. I'm going to label my points. I think I forgot to do that on the last one. And so we have point A, B, C, and D. All right, so this is how transformations affect our graphs, just like they did before. All right, let's look at one more. We're going to look at -2 to the x plus 3. All right, so we're going to start with, again, our basic function. We're going to, because it is 2 to the x, I am going to go ahead and go -1, 0, 1, and 2. We still have our same y values. We have 1/2, 0, 2. No, sorry. 1/2, 1, 2, and 4. All right, for this one, I have nothing inside the exponent with my x, so there is nothing horizontal going on here. Vertical, we do have two things going on. The first thing that I want to do is I want to reflect. This is a vertical reflection. Which means that we are going to be doing something like this. And so this is about the x-axis. But remember that all this means is we are going to multiply our y's times -1. The second thing we have is we have an add 3. And so after we change the signs of our y's, we want to shift up 3. We have our original horizontal asymptote is 0. And so now let's go ahead and see what happens to this. Now you can do this in 1 or 2 tables. I'm going to do 2. And so the first thing I'm going to do is just reflect my y's. My x's are going to stay the same, -1, 0, 1, 2. And we just want to change the values of our y coordinates. And so we get -1/2, -1, -2, and -4. So in this table, all we've done is reflect. All right, and then we're going to go ahead and go to our final table. And what we're going to do is we're going to do our shift now. Again, our x's are going to stay the same, -1, 0, 1, 2. And we want to add 3 onto each one of these numbers. And so if we do -1/2 plus 3, we get 2.5. -1 plus 3 is 2. -2 plus 3 is 1. And -4 plus 3 is -1. Now when we reflect, our asymptote stays the same. But when we shift, it does change. And our asymptote does go up 3 as well. And so we have a horizontal asymptote of y equals 3. All right, if we go ahead and graph this now, I'm going to start with my asymptote. We have an asymptote at y equals 3. And then we want to go ahead and plot our points. So we have -1, 2.5, 0, 2, 1, 1, and 2, -1. And so when we graph this, it should look something like this. Now, of course, in the homework, these are going to be multiple choice problems probably. And so I do recommend, don't just look at the graphs, do the work in terms of recognizing the transformations. And I do encourage you to make a table of values and figure out how those transform. All right, that finishes off this first part of our exponential function discussion. We have one more discussion of exponential functions, and so we'll look at that one next.